So the fireplace automation project working really well. Fan works, fireplace works, all that's good to go. I thought I'd use this video to talk about an interesting challenge during the software development process and how I solved it. So let's go to screen capture. It occurred to me that before I show the code behind this project, a little bit of a refresher was in order. Recall that I am using the base HTTP server module in Python, and if you don't know anything about HTTP, the internals anyway, it is a stateless protocol, and that means it doesn't remember anything that happened once your session is done. So in other words, you make a connection to the HTTP server, you either pull back some information or you push some information up. Once that's done, the connection is severed and nothing that transpired is recalled. So this presented an interesting challenge when trying to get the fan going on the fireplace, because the dimmer module requires a persistent pulse width to be sent for the duration or the full period that you want the fan running. With my process being wrapped around or wrapped up by HTTP, each time I'd make a connection, turn the fan on, once the session ended, fan would go off. So found a particularly cool way to solve that problem, and I'll give you some details on that in the next segment. All right, so with that HTTP refresher out of the way, let's take a look at a little bit of code here. So here's the Python code that runs as a server process in the background. And you can see here we've got a couple of functions. Well, we define a class using the base HTTP server, and within that we handle gets with this code here, and we handle posts. So, and all this works great. The challenge, because of the fact that your HTTP session, or any HTTP session, once the work is done, that session goes away. So anything that you do within it is ephemeral. You know, none of the state remains. So the problem that we ran into, and I've described that maybe described that in the refresher that preceded this segment, is that the little voltage relay or dimmer switch that we have in our circuit, in order for it to deliver current in the proper way to the fan motor, it needs to send pulse widths, electrical pulse widths, and that needs to be done on a continuous basis. It's not like you can, you know, like if I go to code here, where is it? What is it? Do switch. It's not like you can go here and say, you know, this is not the exact pin, but you can go here and say output, set the pin, the pin that you want to deliver the pulse width, set it to a value, and then it'll just keep doing that forever. No, your process has to continually keep that pin in a state to deliver your specified pulse width or duty cycle, as it were. So what I was finding is that every time I'd enter this function and we'd hit this decision making here, when you go ahead and turn the fireplace on, when I have the code in here, by itself, it would, not the fireplace, it would turn the fan motor on, but as soon as the process exited, or my session ended, the fan motor would go off. So it's like that didn't work so well. So enter Python's ability to do threading, right? Handle multi-threading. So what I decided to do was to create a body of work. I'll go down to the bottom here. I call it hold duty cycle. So in here, this body of work will set up the pin that we're going to use for sending the pulse width. We set a variable that we'll use to actually start the duty cycle for delivering the pulse width. And then you notice we sleep for just under a second here, and then we actually stop the process. We stop our duty cycle. Why do we do this? In the process of developing this solution, I learned that I don't know if this is a bug in the GPIO module or not, but what I learned is when I initially start the duty cycle in this way, the fan motor spins very slowly for whatever reason. And so I found that if I stopped it, and I'm doing all this interactively as I'm going through the troubleshooting process, if I stopped the fan motor and then started it again with the same exact parameter, it would then spin at the expected rate. So what I do in this body of work, stop it initially, sleep, and then start it again, and that gets me to the speed that I want it to run. After that, this thread will simply take a look at that pin that we allocate a pin on the Raspberry Pi that we use to determine whether or not this thread should continue to be active. If this pin is false, then we continue in this loop. So the state of this thread will remain, and as a byproduct, it'll continue to generate the pulse widths necessary to keep the fan going. If this pin goes high or becomes true, value 1, then this loop will die. We will stop our duty cycle, set the pin that we use to turn on the fan to output, and then set it to high, which will turn the fan off. If you are not familiar with the Raspberry Pi and voltage relays, typically the voltage relays are active low. So you may have recalled earlier in code, we set the GPIO pin to low to turn the fan on, or to set the pin high, or set the pin on, and then we set it high to turn things off. So that's what's going on here. This thread will run for as long as that monitoring pin is low or 0. Once we set it to high, this loop terminates. We fall out of the loop, stop the duty cycle, set up for output, and then set the pin to high. Thread will terminate, and life is good. If I go back up top here, so we have a condition that we call pulse.
It's dinner time.
And my wife has Google ringing the dinner bell, so I'll wrap this one up. But we send various attributes here. We key on pulse and the off action. This, again, since we are active low, it turns out that in code, when we send the quote-unquote off action, we're actually turning the fan on. And then if we send pulse with a command action of on, deactive high, we come here, We set the monitoring pin to be output. We create another thread, pass a value to the monitoring pin, start that thread, send the parameter value 1 or true or high to set the pin state high, and that is what causes that while loop down at the bottom to terminate, because our thread will see that the pin is now high or true, fall out of the loop, clean up the pin, turn the fan off, and life's good. So yeah, that's a little insight into how I went about solving that particular problem with the transient state of HTTP sessions and my need to continuously send a pulse width to a Raspberry Pi pin to keep a fan going. So interesting to me. Hopefully you found it interesting, and maybe it will help somebody in the future. All right, I'm gonna go eat dinner. Take care.